Good day once again, everyone, and we are back together looking at November 2022 exam. All right, we're looking at chemical equilibrium. We still have quite a number of questions to go through. So if you haven't subscribed, please just make sure that you are part of the family. And of course, you can always join in as a member. Okay, that way you make sure that your uncle is supported, but at the same time, you benefit from the valuable perks that we have for you. All right, so let's have a look at this question. So they give us question, the carbon, carbon reacts with sulfur according to the following balanced equation, right? It's given there with delta H greater than 0. It tells us this is an endothermic reaction, right? So it says the system reaches equilibrium at temperature T in a sealed 2 cubic decimeter container, right? The Kc value is 9.4 at temperature T. Right, so the first thing is they ask us to state Le Chatelier's principle. I'm not going to write that one down, but we know that in a closed system, right, if one of the factors that affect equilibrium changes, then equilibrium will react in such a way as to cancel the change and a new equilibrium will be established. Okay, of course, there are different ways of stating that. You can follow whatever feels comfortable with you as long as we're all saying the same thing. Right. Now, they say at equilibrium, 1 mole of carbon disulfide, okay, is present rather in the container. They want us to calculate the concentration of sulfur present at equilibrium. Now, ladies and gents, please just remember. All right, so what essentially happened in this case is that we are given, the Kc value, right? And note that you've got two gases, right? Which is sulfur as well as carbon disulfide. So what we're going to do is we're going to say, well, what is our Kc equilibrium expression, right? Equilibrium constant expression. So Kc is the molar concentration of carbon disulfide. Okay, right, that's a gas. Okay, that's the products divided by the molar concentration of our reactants, right? And we know our reactants in this case, carbon is a solid, so we don't include it, right? But we're going to definitely include sulfur, which in this case we're going to say that is squared, right? So in this case we know that this is going to be 9.4, that's our Kc value. Okay, carbon disulfide, we know that we've got, in fact, we had 1 mole of carbon disulfide, so we're supposed to calculate the concentration, right? So we know how are we going to get the concentration. That's number of moles divided by volume, right? So we know our volume is 2, so the concentration of carbon disulfide rather, that's number of moles divided by volume, so that's going to be 1/2, right? Number of mole divided by the volume, which is 2, and we're looking for the concentration of sulfur in this case, and we said this is squared. Now remember, all we do is just to cross multiply. Okay, so that would be 9.4 times the concentration of sulfur, right, squared, would be equal to 1 times a half, so that would be 0.5, right? Okay, so we're going to divide both sides by 9.4 and take the square root. Okay, and what does that give us? So we're going to say 0.5 divided by 9.4. We get that answer there, and we take the square root of that answer, and we get 0.23. So it means that the concentration of sulfur at equilibrium would be 0.23. Remember, this is concentration, so that's in moles per cubic decimeters. Okay, so I hope that made sense, ladies and gents. So I'm just going to make some space there. So remember, we use our Kc value, right? We're given a mole in this case. We're supposed to convert into concentration number of moles over volume, right? And that's how we got that 1/2 there, right? So I hope that makes sense, ladies and gents. Right, so they say to us the volume of the container is now doubled at temperature T, and after a while a new equilibrium is established, right? So remember, in this case, once you change one of the factors that affect equilibrium, of which temperature is one, right, then equilibrium in this case will be shifted, it will be disturbed, but a new equilibrium, as we said, will be established. Now they say to us, how will the amount of sulfur change as this new equilibrium is established? Choose from increase, decrease, or remain the same. Now remember, because we are dealing with an endothermic reaction, right? So what does that mean? It means that the forward reaction requires temperature, heat. Okay. If you look at my videos on this, I use that Pac-Man method, right? So Pac-Man facing on the left means that heat is on the left-hand side. So what does that mean? It means that the forward reaction is endothermic, right? So the moment we increase temperature, we favor the endothermic reaction. So it means that the forward reaction will be favored, right? So what happens? It means carbon disulfide will actually increase. It means sulfur, in this case, will definitely decrease. So with an increase in temperature, so we know in this case this will decrease. Okay, right. So 6.4, they say explain the answer in 6.3 in terms of Le Chatelier's principle. Now, remember, in Le Chatelier's principle, you will state the change, which reaction is favored and why it's favored, okay, and you'll state the result, right? So, an increase in temperature, okay, will favor the endothermic reaction. Okay, that's a statement of fact. Okay, endothermic reaction. Okay, the forward reaction is endothermic. The forward reaction is endothermic. Therefore, the forward reaction will be favored, right? The forward reaction is favored. Okay, and of course, in this case, this will lead, or you can say equilibrium shifts to the right. Okay, so this will result in a decrease in reactants, right? In the reactants, which means that sulfur rather, will actually decrease. Okay, right, so therefore decrease sulfur. So sulfur will definitely decrease. All right, now let's go on to the next one. They say to us, if the concentration of carbon disulfide changes by X, right? So it means from what we had before, it is now going to change by X amount, right? They say write down an expression for the equilibrium constant in terms of X. Show all you're working out, right? There's no simplification or solving of XE that is required. Now, ladies and gents, okay, so let me just make some space. So what we're going to do is, just go back to that table method. You call it the ice table, some call it the rice table, right? Whatever you decide to call it. Okay, so we know we've got the initial. Now remember, what will be our initial amounts? It will be what we had at equilibrium, the initial equilibrium, right? Okay, so that will be in moles. In fact, because I already have it in moles per cubic decimeter, please allow me to do so, because they do show that the change is in moles per cubic decimeter. So there's nothing wrong with having this table in concentration. So we've got the change that takes place there. That will also be in moles per cubic decimeters, and that will be equilibrium, right? That's in moles per cubic decimeters. So that simply means I won't necessarily require this portion here, because everything will essentially be in moles per cubic decimeters. Now note, what do we have? We've got carbon, we've got sulfur, and we've got carbon disulfide. So we've got carbon, remember this is in solid form. This is 2-sulfur, which is in gas form. And we've got carbon disulfide, which is also in gaseous form, right? Now, I may not necessarily need this guy. They haven't given me information on carbon. But think about it, the expression will not necessarily require us to have carbon, right? So, in our initial equilibrium, ladies and gents, I want you to remember this. So what did we have in the initial equilibrium? We found that the amount of sulfur was 0.23, right? So that is what we will start with, okay? And you remember that the amount of carbon disulfide started as 1 mole, right, at that previous equilibrium. But in this case, we said concentration would be 1 divided by 2, so that would be 0.5 moles per cubic decimeters, right? That would be the initial concentration of carbon disulfide. Right, now they said to us that the carbon disulfide changes, right? Of course, what type of change took place, right? We know that in this case, it would have increased, right? So we know this guy increased by an X amount. Remember, when we increase that temperature, we favored the forward reaction, right? So it means that the amount of carbon disulfide will actually increase, right? Now remember, in this case, this is where we use our, our ratio, right? So if you had a change by X amount for every one here, all right, let me just, I want to change color to this, okay? So if I change by an X amount, right? Well, the ratio is for every 1, there's 2, right? So if I change by 1x, then this changes by 2x. Okay, why? Because our ratio is 1:2. For every 2 of those, there's 1. So for whatever amount of carbon disulfide that I will change by, the amount of sulfur that will change in this case will be 2, right? So that will be 2 and that's 1. So for every x, there'll be 2x. All right, and then finally, right, so I know that the amount of carbon disulfide I will have, I started with x, I formed x, right? I started with 0.5, I formed x, so at the end I will have 0.5 plus x, okay? And of course, sulfur in this case will decrease, so I started with 0.23, I actually decreased by 2x, so what you have is 0.23 minus 2x. Remember, you would have used the reactants, right? In this case, in order to form the products. So now, ladies and gents, what we're going to have is the Kc expression. So Kc, molar concentration of the products. Remember, we said our products, carbon disulfide, okay, no, not squared, because we have a coefficient of 1, divided by the molar concentration of our reactants, that's sulfur, and in this case we square it because remember, in this case the coefficient is 2 there. Right, ladies and gents, if you still don't understand this, please go and watch our videos on chemical equilibrium, and I promise you they will heal you quick, fast, and in a hurry. So that will be 0.5 plus x divided by 0.23 minus 2x, and that is squared. Remember, they said we do not need to solve. In this case, they said no simplification is required. They just wanted us to have an expression for that Kc value. All right. So I hope that makes sense, ladies and gents. We increased temperature for an endothermic reaction. So we favored the forward reaction. It changed by an X amount in this case, and that is what we indicated there. I hope that makes sense, right? As we move on to the next question. So they say to us the reaction rate versus time graph below represents further changes made to the equilibrium mixture, right? They say the volume of the container is kept constant. So that means whatever it is that was changed, they actually kept the volume and hence the pressure constant. Okay, right. Now, we note at TB in this case, what that simply means is that we either would have changed the concentration, right, or we changed the temperature in this case. Why? Because they said to us the volume stays constant. Okay, right. So let's start. If I look at time TB, right, if you note there, you can see that there's a rapid rise in the rate of the solid line, which is the forward reaction, right? So there was a rapid increase there. So I would think that there was a change in concentration here, right? And the reason for that is simple, because once you change temperature has a tendency of changing both the forward and the reverse reaction initially, right? And then what happens is that obviously equilibrium would therefore start shifting and so on, right? So when I look at TB, in this case at time TB, then I know it's concentration, and definitely in this case that looks like temperature, because can you see both rates actually decreased initially, right? We'll talk about that as they ask the question. They say, what do the parallel lines between TA and TB represent? Well, they simply represent that we are at equilibrium, right? So the rate of the forward reaction is equal to the reverse reaction. So they represent equilibrium, right? So, or you can simply say they represent, in this case, chemical equilibrium, or you can say they represent the rate of the forward reaction being equal to the reverse reaction, right? So 6.6.2. Okay, so they say what change was made to the equilibrium mixture at TB, right? So I would say, now if you think about concentration, remember that only gases and aqueous solutions can be, quantified in terms of concentration, right? So there's no way that we added a solid in this case. So definitely we actually added more sulfur, okay? So we increased the concentration of our reactant. So there was an increase in concentration of sulfur, okay, of sulfur, or you can say of your reactant, okay, reactants. So in this case, the only one that you can increase concentration of is sulfur, right? So 6.6.3, they say give a reason for the sudden change in the reaction rate at TC, right? So TC, definitely note that you changed, in this case, reaction rate started decreasing. So the only way we can decrease reaction rate for temperature is if we decreased the temperature, right? So there was a decrease in temperature. Okay. Right. And they say to us, fully explain your answer in 6.6.3. Now, here's another thing that I want you to note. So a decrease in temperature, ladies and gents, will actually affect the endothermic reaction the most. And you can see how severely the forward reaction was affected, right? But in this case, what happens? In this case, it started actually picking up, right? So it would decrease. So then, according to Le Chatelier's principle, right? Remember, once you change the temperature, right? We favor, in this case, we decrease the temperature. We're going to favor at least a decrease in temperature will favor the exothermic reaction. So the reverse reaction is exothermic, and that's why it would be favored in that case. You can see that the reaction rate for the forward reaction, for the reverse reaction rather, decreased there, and whilst for the forward reaction it started to increase gradually. Right, so we are going to explain that part. Okay, right, so a decrease in temperature, right, will favor the exothermic reaction, right? Okay, so we note that the reverse reaction is exothermic. Okay, and so the reverse reaction is favored. So therefore, reverse reaction is favored. And in this case, that is what caused the forward reaction, or rather that increase there in terms of the forward reaction. Okay, so therefore, in this case, that would increase, in this case, the rate of the reverse reaction. Okay, of the forward reaction. Okay, so that would increase the rate of the forward reaction. All right, so ladies and gents, please note, when we, as I said, you state the change, which reaction is favored and why it's favored, and then you state the result in that case. So you note in this case that we are looking at the reverse reaction. We're looking at the change in temperature, and so that's why we stated what we stated. And please note, both the forward and the reverse reaction were severely actually the forward reaction was severely affected, okay, in that case. So, and that is why we were saying that temperature will actually affect both of the reactions. Okay, right, so we are going to keep it there. I hope that you understood this. Please, if you have not subscribed, please make sure you do the right thing. Okay, and the favorite uncle will always make sure that he does what he does best. All right, otherwise I will see you guys next time. Sharp, sharp.